Good evening, everyone. Good morning, Dr. Jean. In this short course on 20 February 2025, the short course title is Introduction to Distributed Acoustic Sensing for Geophysics. It's in the framework of the webinars or the afterworks of the EAGE Local Chapter of Paris. EAGE was founded in 1951, which is a non-profit association for geoscientists and engineers. The main goal is to promote development, innovations, and application of geoscience and related engineering subjects to foster the communication, fellowship, and cooperation between those working or studying or interested in the field of geosciences. The next annual meeting of EAGE, which is the 86th conference and exhibition, so we are approaching to 90, will be in Toulouse, in France, in the June 2025. You can see the website for the topics and for more precise information. Call for abstract is already closed, as far as I know, and usually we have more than 6,000 participants, more than 1,300 presentations, more than 200 exhibitors, and it's a really big event on geosciences in Europe. The very next conference of EAGE, named 5th EAGE Digitalization, will be in March, Edinburgh, in about 1 month. So again, you can
You're muted.
Thank you. So there are several local chapters. We are located at Paris, but we have other colleagues who are in the other cities in Europe, and also, for example, in Azerbaijan, also in Kuwait. The EAGE local chapters are not limited only to European countries. The team in Paris, the president is Laura Mosga, Vice President Emilio, Treasury Guillaume, me, Pedram, as Secretary, and the other colleagues, Said, Soraya, Imen. And as you can see, it's a multicultural and also a multidisciplinary team from different domains of the geosciences. We are collaborating in proposing some local events like this one, even if the lecturer has kindly accepted to participate from the overseas, from the States. Last year, we had the chance to become the best local chapter. That we won the prize in the EAGE annual of the last year in Oslo. Because of the events that we had, lots of the events that we had, like this one that we have together. The very next event that we can promote it is in April 2025. It's very close to what we will see today. It's a DAS, from design to data recording and process. The registration is not yet open. I invite you to follow us on LinkedIn to receive the latest information and to register. But about the short course that we have today, it's an introduction to distributed acoustic sensing for geophysicists. After my opening, I will hand over to Dr. Jean from Colorado School of Mines. And the short course will have 4 parts: DAS fundamentals, DAS seismic applications, DAS geomechanical applications, and discussion and conclusion. After presentation, we will have Q&A session. During presentation, if you want to add your questions in the conversation, please do not hesitate. And at the end, we will follow the questions to answer them. So in the first part, dust fundamentals, we'll talk. Dr. Jim will present about measuring principles and some optical phase to strain rate conversion. And in the application part, about dust measurement of seismic waves, microseismic event example, application of dust in hydraulic fracture imaging, and earthquake monitoring. In the geomechanical applications, we will have the use of dust low frequency to monitor slow subsurface deformations or monitoring of hydraulic fracturing propagation, landslides, volcano monitoring. And to present Dr. Jim, we have the privilege of having him today, this evening. It's morning for you, at the end of the morning. Geophysicist graduated from Columbia University and Pekin University. Associate Professor of Geophysics at Colorado School of Mines, co-director of Reservoir Characterization Project. He was a SEG Distinguished Lecturer last year. His expertise, distributed fiber optic sensing applications in geosciences, seismic imaging and interpretation, unconventional reservoir development, machine learning applications. So please share your screen.
Sure. Thank you. Thank you for the introduction, and thank you for the invitation. Actually, I will try to share the window instead of the full screen, but were you able to see the presentation okay this way?
I see the EAGE, yes, exactly. I think everything is fine.
Okay, so and also what I'm planning to do is also I will have a laser pointer. Are you able to see the move of the laser pointer this way?
Perfect.
Okay, perfect. Great. Yeah, so then I will start. And thank you everyone for joining. This is a huge audience, and I'm very flattered, and thank you so much for joining me today. So today I will basically give an introduction of dust, and more specifically for geophysicists. Yeah, so time is short, and let's get to the fine part. So as Padrin mentioned, that we'll start with introducing dust. So because this is a short course, I will dive a little bit deeper and a little bit more fundamentals. Then I will basically focusing on two large envelope of applications. One is a seismic application, the other is a geomechanical application. So I'll learn a little bit more when I get into that before we conclude, and then I will answer your questions. Okay. So I probably won't answer question during the presentation just for the time purposes, but for all the slides, you should be able to find the slide number here. If you record a slide number and write down your question, I should be answer all of them afterwards. So I will start with introducing, because we all know that distributed acoustic sensing is a kind of distributed fiber optic sensing. So that basically means that we need to first talk about the optical fiber, right? So what is a optical fiber? So if you use internet, you probably should know something about the optical fiber. The reason that most of you are outside the US and you are able to see me in real time is basically because the optical fiber that the company deployed globally to transfer the internet data. So we heavily rely on optical fiber for internet transportation and for internet data transportation. And there's a massive production. As you can imagine, there's a massive manufacturing of the optical fiber happening globally as well. So, however, if you zoom into a optical fiber, and so the structure of it is really simple. So it's basically just two layers, and one is a core, a fiber core, and the outside is a so-called cladding, right? So you don't have to remember this terminology. All you need to know is actually we're forming a structure with a slightly lower velocity material surrounded by a higher velocity material. So if you're a seismologist or working with waves, you know that this type of structure form a really nice waveguide and can trap energy inside. So the energy of light will be trapped inside the core and propagating over very, very long distance with minimum energy loss. So this is the whole goal of the fiber optics is try to propagate the signal over a very, very long distance. And also, we have fiber everywhere, right? So here is actually a existing fiber network, and this is only showing you the major connection points. So if you zoom in this map, there will be a lot of more showing up. So we basically have fiber almost every single block, every single town, almost globally, right? So but also, because the fiber itself is fairly cheap, and also there's, already very well established way to deploy the fibers, you can deploy the fiber yourself pretty easily. So this is actually a test that we did at the Cross Gold Mines, and all we do is really, buying some fiber cables and laying them on the ground. So all of a sudden we found we are able to do some surface wave measurement using these fibers. So deploying fiber is relatively easy, especially if we compare that with the traditional sensors. And also another benefit, especially for the oil and gas industry and subsurface industries, is if you protect the fiber with a mechanically strong cable, something like this design, then you are able to deploy your fiber along, any type of well, along the entire well length. So all of a sudden, you are able to make sensing of, of your entire well, and you can be able to put the sensor really, really close to the rock and to the formation that you care about. So this is really beneficial and actually enable a lot of applications. But then the next question is, what black magic does fiber optic sensing do, distributed fiber optic sensing do, to be able to measure physical changes along the fiber, right? Actually, if you look at the principles, there's a lot of engineers' effort behind it. But if you just focusing on the principles, it's actually fairly easy. So, if we come, so I have a optical fiber that being installed on the surface in the well, already exists there. I connect one end of the fiber with an instrument, usually we call it the interrogator. And this interrogator or this instrument will start sending laser pulses into the fiber. And this laser pulse, very short duration, is probably just 5 to 10 nanoseconds. And this laser pulse will start to propagating down towards the end of the fiber, or propagating along the fiber, as what the fiber is supposed to do, right? So this is how we do the internet transportation. I send the laser pulse here at the end at the other end of the fiber. I'm able to receive that pulse with a very minimum energy losses. So, however, just like everything in the world, they are not perfect. Fiber is not perfect too. So, as we manufacture fiber, unavoidably, there will be always some heterogeneities that are built in the fiber. So, which means that as the light that is propagating along the fiber, every piece of the fiber are able to scatter and then reflect a little bit of a very, very small portion of the injected energy backwards. So this energy. So now think about the flow, the laser propagation path, right? So you have a pulse propagating forward, but every single part of the fiber will reflect a little bit back of the energy backwards. So if the interrogator also have a built-in receiver in it, and to receive this so-called backscatter energy anywhere, right? So now you think I send a pulse, and then all of a sudden I start to receive a time series of backscatters along the fiber. Because we know the speed of sound of the inside the fiber very well, because we manufacture those fiber, and we and also can easily measure the time delay between we sending this pulse into the laser, into the fiber, and the time delay of a certain backscatter arrive back to my interrogator. So this time delay between these two actually mark the two-way travel time of that particular backscatter that experience in the fiber. So again, you'll find this, if you're a geophysicist, you'll find this extremely similar to the reflection seismology, that if I know the speed of the wave, if I know the delay time, I can easily locate where this backscatter happened along the fiber. And because every piece of the fiber are backscatter some energy, that means that with a single pulse into the fiber, I'm able to receive and locate the backscatter everywhere along this fiber. Okay, so that's the first step you need to do. And if we look at the backscatter, actually contains really rich information. Again, I won't be able to, due to the time, I won't go into a very detailed technical detail about this. But what you need to know on the very high end is that there are different type of backscatters, and they represent the different wavelengths being reflected. And there are Raman backscatter, Boolean backscatter, and Rayleigh backscatter. So, we won't go into details, but the nice thing about this different type of backscatter is they all sensitive to the temperature and the strain of the fiber where this backscatter happened. So based on their different sensitivities, people have developed different technologies that include distributed temperature sensing, distributed strain sensing, as well as the distributed acoustic sensing, which we're mainly focusing today. So the benefit of this is really we can measure temperature, strain, and vibration everywhere along the fiber continuously in both space and time, and also with a high resolution in both space and time. So this is really the benefit of distributed fiber optic sensing can give us. With a fiber that deploy anywhere we want it to be, with the instrument connect to one end of the fiber, all of a sudden I'm converting this fiber into a very dense array to measure temperature, strain, and vibration. So I always feel like, a lot of when each time I instruct into this, a lot of students get a little bit confused that what do you mean by continuously space and time, temperature, vibration, strain? That's a lot of information, right? So the easy way I find that people can understand it, just think about your skin and think about your arm, right? So our arm and our skin is a natural distributed fiber optic sensor, let's call it that way, even though it's not based on fiber, but it's a naturally distributed temperature, vibration, and strain sensing. So if I close my eyes and if I put the ice cubes anywhere along my arm, immediately I know when and where you replace that ice cube, right? I can also tell how cold that ice cube is. Same thing for a pinch, which is a strain sensing, basically measure whether the fiber is compressed or extended anywhere, anytime, or a vibration, right? So if you have a phone, it's ringing, and then you put it in here, immediately you will feel that vibration as well. So now think about we're converting the capability of our natural skin to a fiber, and then we're able to deploy this fiber everywhere, right? So all of a sudden we're able to look at this world in a very, very different way. And we're able to tell a lot of phenomena that we're not able to capture before. So this is really the power of distributed fiber optic sensing. This is something I spent 10 years on and still fascinating by the development every single day. Okay, so now let's dive a little bit. So this is a big picture of the distributed fiber optic sensing, but today we're mainly focusing on distributed acoustic sensing, right? So because this is a short course, I feel like I'm entitled to be able to put a little bit equations into this presentation, but don't be scared because they are very, very simple equations, okay? So think about the wave equations, and we're talking about just 1D propagating wave. The simplest form of a wave equation. So in a very general form, right? So the light that propagating in a fiber can be considered as a 1D propagating wave that can be represented with this very, very simple equation. So this is a plane wave equation mimicking 1D propagating, and we have an amplitude term. We also have a phase term. And this phase term you can see is changing with time and changing with space, and also changing with some static phase, which represents some random structure of the fracture at a certain backscatter location. So you can see the wave that starts from the interrogator and propagating at a certain location at Z, and then being backscattered. The moment it's backscattered, this will be the phase that of this wave. But of course, the way that we can receive this backscatter is we put the receiver at the interrogator. So the wave means that the wave had to propagating backwards to the interrogator. So we have a two-way travel time here, right? And then you can see that basically just adding another wave number times the distance, another z into this in terms of the phase term. Okay, so far it's easy, right? So now here's the magic we're going to do with DAS. What we'll do is we'll compare the phase difference of the two backscatters that's separated by a distance called gauge length. And we call this gauge length, let's use L to represent this gauge length. So based on the previous equation, you can see the backscatter I received, all receive an instrument, the backscatter happen at Z, have a phase like this. So it's basically, we can ignore the time term, the basic KZ plus a static phase. And the phase of this L plus Z plus L location is similar, exactly the same thing. The only difference is you need to add a 2KL because it does travel a little bit more than the previous backscatter. And also the static phase can be different because the fiber structure can be very different from here to here. Okay, so if we're measuring the phase difference between these two, and in the optical world, there's many ways you can measure phase difference of two injecting light. So this is not a problem. So if we're looking at the phase difference between these two, and you will find actually the difference of them is 2KL. So because the second backscatter travel 2 times 2L actual than the first one, and also a static phase difference of these two fibers. Okay, so that's the second step we need to take. Now is the third step. Now I need to send, instead of one pulse, I need to send the two pulses sequentially. And these two pulses can be separated just by, for example, 0.1 milliseconds. So usually, when we're doing DAS measurement, it's very common that we send about 10,000 pulses per second. So it's sending a lot of pulses very, very quickly. So however, in my first pulse, so this is basically the phase difference between these two locations. And after I send my second pulse, let's assume that this portion of fiber experience a very, very small deformation. Very, very small deformation. Let's call this deformation delta Z in here, right? Then I find actually, because this delta Z is really small, so it won't change the static phase. However, the second pulse, the phase difference between these two locations becomes 2KL plus 2K delta Z, which is the actual length that the second pulse need to travel due to a local deformation of the fiber, plus the static phase. Okay, if I'm taking the phase difference between these two pulses, right? So now you think we take 2 times difference. One is in space. We take a phase difference of the backscatter in these two locations. We also take another temporal difference of the phase difference between these two pulses. And you will find that all this unknown term cancel out. The only thing left is a 2K times wave number times the delta Z, and delta Z is how much this fiber locally is being extended or contracted. So this is actually the magic, right? So if we continually sending pulse, we can measure a phase difference between second pulse and first pulse, and we can also measure a phase difference between the third pulse and the second pulse. Each measurement, each pulse, sequential pulse, will then be able to tell us how much of this section of fiber is being extended or compressed. Also, if we scale this delta Z with the L, that is the gauge length, then we can see that whatever measure the phase difference we're measuring here is linearly proportional to the strain rate of the fiber experiencing at that location. So this is actually, the magic that does play. Even though it is called distributed acoustic sensing for the historical reasons, but what is really measured is it is a dynamic string rate sensing, distributed dynamic string rate sensing. right? So this is what exactly is measured. And also this phenomenon, this fundamental is really impacting a lot later on when we're discussing a lot of observations. Okay, so this is, we're still in the optical part, but if you get confused by this, you can watch the video later on. But at a very, very high level, what you need to remember is DAS measuring string rate. And the string rate by itself is the deformation or displacement, take a spatial gradient and then take a temporal gradient to get the string rate. Okay, so this is the fundamental of the DAS will have, right? So of course you can easily find in the literature, and you'll find this is a linear equation conversion from the phase to the optical. All you need to do is just adding a constant that can easily calculate it from your fiber setup. Okay, so the next step, what the geoscientists, geoscientists are okay, cool, string rate measurement. So how are we gonna use it? The first thing we can use it because it's a string rate measurement, but with very, very high frequency, right? Remember, we're able to send 10,000 pulses into the fiber, and each pulse can measure the entire fiber. That means that everywhere along the fiber, we're able to measure the string rate at least 10,000 hertz, right? So that's more than enough for most of the seismic studies. So that basically means that we are able to use dust to pick up seismic waves or to measure seismic waves. So this is great, but but I have geophone to measure seismic wave too, right? I have 3D seismometer to measure seismic wave. Why I want to use DAS? And more importantly, how does the DAS measurement different from our traditional geophone measurement? So there's one big difference. Is the difference is caused by the geophone, whether is a accelerometer or is a velocity based geophone or is a or is a deformation or displacement based geophone. What they measure is particle motion. Basically, it means how the ground move at that particular location. However, what the DAS measure, as I explained it previously, we measure string rate, which is the spatial gradient of the particle motion at that location along the fiber direction. So that's actually bringing some complexity into the DAS measurement in terms of the seismic wave. Because again, let's go back to this very simple plane wave equation here, right? So I have a plane wave propagating, and this is represent the amplitude and the phase term of my plane wave. So this is how we usually represent seismic waves. We have a particle velocity, so it's represented by a single location. However, the string rate need to take a spatial gradient of this. So if I take a spatial gradient, you find actually the wave number comes out and combined with the amplitude term. And also you have an imaginary I term here coming out. So the imaginary I term represent 90-degree phase shift, right? So if you're a seismologist, you probably know what I'm talking about. If you don't worry about that. I'll explain that later. And then you're also being scaled by the wave number as well. So this immediately you find, okay, so the amplitude won't be different, the phase won't be different if we directly compare DAS and the geophone recorded at the same location. However, things got even more complicated if the wave that hitting the fiber with a certain angle, which is very common and in the seismic acquisition or seismic recording. So in this particular case, let's say if the angle between the wave propagation direction and the fiber is theta, based on the same phenomenon, based on the same idea, right? If we look at the string rate implemented by this plane wave that propagating at this direction, we follow the exactly same idea. You will find that not only I need to project the particle motion amplitude to this fiber direction, but I also need to project the wave number, which is also a vector, to this fiber direction as well. If I combine these two together, I find the string measurement on the P wave. So there you can see this is a P wave because the wave particle motion is aligned with the wave propagation direction. Actually, it will give us a cosine square sensitivity. So if you're familiar with a geophone measurement or seismometer measurement, if it's a single seismometer, the sensitivity change with the incident angle or change the wave propagation direction have a sensitivity of a cosine. So this is the angle sensitivity we'll have for geophones. And however, because on DAS is also sensitive to wave propagation direction, it's actually have a squared sensitivity. So that means that as the wave getting more and more vertical towards the fiber, it's propagating up and down, and thus losing sensitivity much faster compared to a single component geophone. Okay, so this is just for P wave. And for the S wave, things got a little bit even more complicated. For a propagating S wave, if we assume a plane wave, for the same idea that we need to project both the particle motion and the wave propagation into the fiber direction. And because for S wave, the particle motion is perpendicular to the wave propagation direction, so that means that basically means that I will basically have a sine theta times a cosine theta comes into my sensitivity. With this will migrate into a cosine sine 2 theta or cosine 2 theta, depending on how you define this angle. So the important knowledge of this is the sensitivity of S wave to DAS actually are much more complex. If we compare a single component geophone, let's say if a horizontal component geophone, I have a S wave propagating downwards, the geophone have the maximum sensitivity. They will basically more sensitive for a vertical propagating wave. However, for DAS, if the wave is propagating vertically compared to the fiber, if it is an S wave, it also have a zero sensitivity in here as well. So this is actually very, very different, and especially in the early stages, bringing a lot of confusion, and simply because DAS measuring string rate instead of particle velocity. Okay, so if you think this is not complex enough, let me add a little bit more additions. So here is a very simple numerical experiment. And what so this was done by my student, previous student, Dr. Alexei Titov. So what he did is he just set up exploration source, very easy. You can done it with Python or any package very, very easily. And he set a line of geophone and also put a DAS on top of the same located line of geophone and DAS. And he want to look at what the geophone and DAS looks like. For the geophone is single component geophone along the horizontal, and the DAS measuring string rate along the horizontal. And here actually compare the difference between the two. On the left is the geophone, and on the right is the DAS. So immediately you see a couple of things, right? So let's take a look at the right-hand side. Clearly you see there's a 90-degree phase shift of the waveform, right? So this basically represents this I term that I'm talking about previously. But also if you compare the polarity, on the left side, the geophone actually switched the polarity over the pendex, right? Simply because the geophone is a single component, it's always assumed right is the positive. And then, so as the wave propagating to the left for exponential source, on the left side, the polarity of the geophone will becomes negative, and then on the right is a positive. However, on DAS, we find that actually the polarity are exactly the same left and right. So a lot of times that when people comparing geophone waveform with the DAS waveform, they find sometimes the polarity of them seems to agree with each other. Sometimes they seems to do not agree with each other. And what causing that? Actually, what causing it is also very simple. Is again, we need to blame that the DAS naturally measures string rate instead of particle motion. So again, for the geophone, if I have exponential source as is radiating out, for the geophone on the left, I should receive a negative signal because the amplitude actually project into negative direction, and on the right-hand side is a positive direction. However, for DAS, we need to also consider the wave propagation direction as well, because the wave number also coming out into the amplitude term. So on the left, the amplitude is negative, but wave propagation or the wave number is also negative. So I have a negative times a negative, it becomes a positive. So I have a positive on the left, and on the right, they're both positive. So this very simple thing actually explains why in the dust we see a consistent polarity left and right, but on the geophone we see it different. So you need to be very careful when you're comparing geophone with dust, simply because dust is also sensitive to wave propagation direction. So I have to talk for completeness. I also need to talk about S wave, right? So because if I have a shear source here and reading the S wave that is basically on the lower hemisphere is moving to the right, I find that in the dust, if I were measuring it using particle velocity, right, over a geophone, I find that on the left and on the right, this S wave should have the same polarity. However, for the dust, we'll find that because on the left, the wave is propagation is negative and the amplitude is positive, the multiplication of this is negative. And on the right, both are positive. So that basically means that as the S wave, S source, a wave that is propagating, there should be a polarity flip happening right at the apex if I'm measuring it along this fiber. Okay, do we observe that? We actually do. So let's combine all the knowledge we have learned this part into this particular simple example, which is a field data recorded by a microseismic event. And in this particular case, I have a microseismic and I have a horizontal fiber. This is actually a fiber installed in the horizontal well and the measuring string along this direction, right? Along the well direction. And I have a microseismic happening here. It's actually propagating with a P wave that propagating faster and S wave propagating slower. So in the dust record, on this dust record, horizontal is along the fiber, that's a project here. Vertical is time. I find there's a P wave arrive first, and we have an S wave arrive later, right? However, immediately, as you can see, we have the S wave polarity that changing across the apex. That's exactly what we predicted as in here, right? So S wave need to change polarity over the apex. However, we also find that the P wave, first of all, is the amplitude decay really, really fast as we're getting close to the apex because the wave is hitting the fiber near vertically, so we're losing the sensitivity. Remember that the cosine square sensitivity. And also, we find that the P wave polarity does change left and right. So this doesn't seem to agree with our synthetic study because we think the P wave should not change polarity on left and right? So however, we need to consider that this is a microseismic event, means that it's a double coupled seismic source that radiate P wave and S wave with a different polarity at different directions. So we can find that there's a multiple polarity flip, the P wave flip polarity left and right, and S wave flip polarity couple times, at the different locations. So, however, we already know that this is basically just due to this polarity flip is not related to source. It's basically related to the dust is measuring strain rate. However, all the other three is related to the source mechanism. So if you're familiar with this topic, immediately you will get excited. That basically means that we're able to do a moment tensor inversion, or we can use the dust data to invert for the source mechanism or the slippage of the source. And this is exactly what you can do in this case, that with a very simple synthetic study that you put a pitch ball, and this basically represent which direction the source rupture. And you are able to predict all the polarities you find, polarity change you find in the data, right? So we can see in this case, we do find the P wave flip polarity left and right. We also find that the S wave flip polarity 3 times, just because of the source mechanism and also plus the receiver response at the apex locations. So you find this is super cool, right? So we're able to really start to getting more understanding of the microseismic or of the earthquake, just because the dust is able to measure the wave field continuously. So we can closely capture how does the wave field change spatially and to back calculate what the source looks like. So, but we can do even more than that, right? We can do even more than that. Because dust measure wave field continuously, we're able to capture a lot of additional phenomena that we're not able to tell or distinguish using a single point sensor. So here actually shows another example, a microseismic example that published by my previous postdoc, Francis Bennett, who is working in UK right at this point. And so this is actually a earthquake that or microseismic that were able to capture the P wave and S wave. You also find that there are some additional signal in here, right? And they shouldn't be there. So why there's a P wave and S wave? What are these additional things? It turned out that these are the reflective wave that caused by some local recently created hydraulic fractures. What we're doing in this particular project is the operator is conducting hydraulic fractures for oil and gas production, and the microseismic is caused by the hydraulic fracture operation. And we can use this microseismic as a active source to image where the hydraulic fracture being created. So this is really cool. It has a good impact on the hydraulic fracture operation, but with a similar idea and with a similar phenomenon, if we enlarge this scale into kilometers to tens of kilometers, we can get even more. So here's a really nice study that I put the group here. I think this is from Rice or Lawrence Berkeley lab. That if you connect the DAS interrogator with a subsurface cable, and people use this, as I say, the reason you can see my presentation right now, if you're not in the US continent, is because all these subsea cables that are doing internet data transportation, right? So if you connect the DAS interrogator with one of these fibers, and you were able to convert this subsea cable into an array of string rate sensor that can capture large earthquake events. So this is basically a seismic event being captured by this array. So you can see a really nice P wave, S wave. You can also see that there are about 10 seconds separation between P and S. That simply means that this event is likely to be that's 80 to 100 kilometers away, right? So that's not the focus. But the focus is that because we're able to measure P and S wave, seismic wave such continuously in space, we're able to identify this local scattered wave at the various location along the cable. And actually this study found a lot of these local scatter wave are default zones, local faults that are previously being mapped or not mapped. So you can see the physical phenomena are exactly the same at a a kilometer scale or thousands of meter scale to tens of kilometers, hundreds of kilometer scale. That we're able to use the continuity, spatial continuity of the waveform to figure out the detailed subsurface structure that we're able to use DAS interrogator take advantage. Now think about if you just have a seismometers or single point sensor, you can still capture this wave, but all you can tell is, yeah, this station seems to be noisier than the other station, but I don't know why. It's only the capability of mapping the string or mapping the wave field with a continuously in space, you can tell or you can interpret this coda wave as a local scatter by a local fault. So this is also really cool, but the benefit of using DAS to monitor earthquake doesn't stop here. So this is also one of my favorite study that published by Caltech a couple of years ago. And what they did is after the Ridgecrest earthquake in California, and they bring an interrogator and they rush to a local fiber provider and they connect the interrogator with couple fibers in the local network. And the fiber is already there. And like I said, you have fiber everywhere in almost all the township, you'll have a fiber there. All you need to do is just find the right person and connect to the fiber. And this group were able to connect to several of this fiber so that they can convert this fiber into a very, very dense geophone array to monitor aftershocks. So it turned out that through advanced signal processing, they're able to, enrich the aftershock catalog by almost 10 times more events. and just because it doesn't really take much to record it, right? So you don't need to deploy the array, you don't need to get close into the earthquake area. All you need to do is just tap into one of the fiber and start recording. So this is a great benefit. You can see for earthquake warning, earthquake monitoring, and also the urban structure monitoring as well. Okay, so that's pretty much about the seismic I'm going to talk about today. I still have 50 minutes and time is just right. So more recently, and the people start to realize that, yeah, that is a string rate sensor, distributed string rate sensor. And I'm able to measure string rate with a frequency that from tens of hertz to hundreds of hertz to even thousands of hertz, right? So no problem. But people also find that that's the instrument of the measurement of that. If you find the correct version of the DAS interrogator and the correct version of the laser, the measurement is extremely broadband. When I say extremely broadband, I'm not talking about like from 1 hertz to 100 hertz broadband. I'm talking about from 1 millihertz to 10,000 hertz broadband. So previously, all the example I show, I'm talking about the DAS recording over less than a second, at most maybe 1 minute. However, the DAS measures things continuously. Like I said, it's continuously in space, it continuously in time. You can make a DAS measurement over days, weeks, and even months, years, as long as you can handle the data I/O, right? You can handle the data storage, which is another topic. But if you have this continuous record, and you just apply a very simple low pass filter and downsample it into, let's say, 1 second per sample. So that means that we're looking at the frequency band less than 0.5 hertz. And all of a sudden, you're converting that into a slow string rate meter. You're still measuring string rate, but you're able to capture string rate that changing very, very slow. So we're talking about hours of data of very, very slow deformation string measurement. So what's that useful, right? It turns out the first usage on this is for hydraulic fracture monitoring. Because as you are doing hydraulic fractures, either for oil and gas or for more recently popularly enhanced geothermal system, right? So we're creating a lot of hydraulic fractures for geothermal energy production. So as long as you're doing hydraulic fracture, you're creating hydraulic fracture in the subsurface, you're also creating a stress and strain field around these hydraulic fractures. This is very easy to understand. You have a continuous material, all of a sudden you put a fracture in there and try to jack it open. Of course, you're gonna squeeze around the surrounding rocks. They won't be very happy, so they have to deform to make space for your fracture to grow. So this deformation characterized by compressional strain on both sides of the hydraulic fractures, so usually we call it the stress shadow, and also a extensional strain around the fracture tip, which is sometimes we call the hardship signal, but this is really more popularly called the processing zone of the fracture tip. So this is a tensile strain accumulation zone that promote the propagation of the hydraulic fractures. So with this, as the hydraulic fracture grow, it will imprint this strain field around it. And if you have a fiber near it, you're able to capture this strain field in real time. So here's an animation I recently used a lot. I found it's very easy for people to understand what I mean by capturing strain field, right? So here I'm actually using a very standard geomechanical model to calculate the strain field created by hydraulic fractures. So in this case, I have an injection well, which is the purple here, blue here, and I have the fracture that is plant that's growing. This is a elliptical fracture as it grow. And then I put in a monitor well that instrumented with fiber and measuring using low frequency component of DAS or any type of distributed string sensing. So I'm able to measure the string perturbation caused by the growth of these hydraulic fractures and along this monitor well. So the data I recorded using the fiber on this well would look like something like this. On the vertical axis, so this is what we call the waterfall plot. On vertical axis is the distance along the monitor well. And the horizontal is basically time. As things propagate, this is what we observe. Okay, is there any questions? If not, please mute yourself. So as the wave propagating and as the fracture propagates, so this will be the string field we capture with time. So then, if so this is synthetic data, and if I'm also adding the fracture closures here, we can also see that in the string real field, we can also capture the fracture closure and also the relaxation of the stress shadow. And we can also see the heart shape and also see the string stress shadow on both sides. And this is the synthetic data. And here is what we measure in the field for real. So this is a real project, real well, and we're doing a real hydraulic fracture monitoring. So in this case, you see the signal we observed on the fiber matches the conceptual or synthetic model really well. We're able to see the harshness signal or extensional zone before the fracture hit. We're able to see the stress shadow, mimicking the stress shadow here. We see the fracture opening during the pumping period, as you're showing here. We also see the fracture closure afterwards, right? So this is really a nice, excellent measurement to understand the hydraulic fracture propagation. So there are multiple ways you can do that, but the simplest way you can do is you can pick the fracture locations. And this is probably the most accurate way to measure hydraulic fracture geometry, simply because we're having a string measurement with a meter level accuracy. So here I actually show you an example of a particular hydraulic fracture operation that we created multiple hydraulic fractures at the same time. So as you can see that on this string remap, this is actually exactly the same data as the previous one. The only difference is I have three fractures that they can easily map out at this location instead of one. But I'm still having a heart shape signal, I'm still having stress shadow, I still have the fracture closure, but I'm able to map multiple fractures along my monitor well. Just by doing this is already super useful because we're able to, because when we do perform the hydraulic fracturing operation, we know where we initiate those fractures. Those are along my injection well or treatment well. And on my fiber, I also know where those fractures landed, right? So I'm able to connect the dots so that I can measure the fracture connectivity and the fracture orientation between these two wells. So on one side, this is extremely useful for unconventional reservoir, oil and gas production, because the fracture orientation and the fracture density is one of the key characters or key parameters we need to consider when we design the hydraulic fracture operation. But you can see this geometry also mimic very closely to enhanced geothermal system, where we need to create a fracture system between two horizontal wells so that we can circulate fluid and harvest heat from the subsurface. So using the fiber, and there are already companies that are doing that, we're able to characterize this fracture system that benefit our subsurface underground operations, right? So this is really cool. It's had a lot of impact, but I think we can go even beyond that. So all this previously shown and all this synthetic model I'm showing with the stress shadow, with all this fracture behavior, string behavior, they're all for tensile fracture. They're for hydraulic fractures. But in the geoscience world, a lot of times we're more care about the shear fractures because they represent earthquake hazard. They represent the damage, right? So we want to monitor faults. We want to monitor fractures that are doing shear movement as well. It's turned out that fiber can also capture shear fractures really, really well with very high spatial and temporal resolutions. So this is a case study we just published this year at the HFTC conference, Hydraulic Fracture Technology Conference in US, actually last month. And in this very case, we demonstrate a few case study in Sichuan Basin, China, when the operator was doing hydraulic fracture operation. However, what we observe on the fiber are characterized by a large-scale bedding plan shear movement together and with a couple of vertical fault reactivation. So, if you don't understand, a lot of the terminology here, basically this is represent a very large hazard for induced seismicity and also potentially for casing deformation. So this is bad. But we're able to monitor very closely with the fibers. You can see this is the string measurement, and the shear fracture, vertical shear fracture, is characterized in the string measurement by this compression and the red and blue compression and extension dipoles that observe on the fiber. You can see we're able to reproduce this very nicely with geomechanical model. So this actually enable us to back calculate or try to invert, understand the very complex fracture network happening in the subsurface. And then you can see, you can immediately see this can be extremely useful for long-term earthquake monitoring. But besides earthquake, we also can do even more. So after the publication of the low frequency component of DAS, people find we can use it to measure very slow string measurement. A multiple group globally are able to use this technology beyond hydraulic fracture monitoring, which is very, very happy to see. So this is a study that that use a similar idea to monitor a landslide in the UK, which is not very far from you guys, and in this case, that they're able to capture this slow string rate measurement, due to a very, very slow sliding of the surface of the near surface materials. So in this case, you can refer to this paper into more details, but you can see that they're able to explain a lot of these string patterns that are due to the different rupture process and also different topography impact of the measurement. So also, even cooler, in my opinion, even cooler is we're able to use this to predict volcano eruption. So this is actually a paper that is still under review. And the author is Jiaxuan Li, and currently a faculty at UH. But he conducted this work when he was a postdoc at Caltech, collaborated with Zhongwen Zhan's group. And so because it's an unpublished work, and I did receive the permit from the author to show just this one slide, so I cannot give too much detail. But in general, what happened here is they are using a existing dark fiber. So this is the fiber used for internet. And they tap one of the fiber and to try to record a volcano eruption in the Iceland. And what they find is when you're using low frequency component of the DAS signal, you find that hours, almost 5 hours before the actual surface eruption, they were able to see this really, really nice low frequency string signal on the surface fiber. So if you look at this, if you stare at this pattern, this is actually a heart-shaped signal that almost identical to the heart signal that we observe in the subsurface. The only difference is the scale is much, much larger. And instead of hydraulic fractures, we actually have a magma chamber that migrating from the subsurface to the surface. So, but it's still a tensile fracture. And the more importantly, the local community are able to use this signal to predict the eruption of volcanoes. So I can see this is, I hope it will be published soon so we can all read it. And this is a very, very exciting development, at least for me, to see how we can further use DAS on the geomechanical work. Okay, so this is just demonstrate that the same idea for hydraulic fracturing, if you just rotate everything and make things much larger, all of a sudden you start to monitoring magma chambers and magma migrations. So today, mainly, so because of time limit, today I can only cover two large applications for DAS. One is on the seismology, and one is on the geomechanics. However, there's also a third large domain of DAS, which I'm also heavily involved with, is to use DAS to measure flow. So we're we're able to use both temperature response of DAS and also acoustic waves and the turbulent flow to monitor, to back calculate the multi-phase flow characters. So I don't have time for this for today, but I did gave a SEG distinguished lecture last year. So and you are able to find the recording on the SEG website as well, right? So, but you can see that's by itself. Initially, people designed it just for acoustic sensing. But all of a sudden, just by exploring the data, we're able to develop so many different applications across so many fields. So I would say, if you want to take something away from today's short course or lecture, I think that is, on the very, very high level, a broadband distributed string rate measurement, right? And they actually are able to provide you with a high spatial and temporal resolution. You can also measure things over very, very long term. So it provides a great opportunity for so many geoscientific studies at a different frequency, the spatial scale, and temporal scales. But more importantly, a single dust you can see can be used by a seismologist, can be used by a volcanics, can be used by glaciologists. So cross-disciplinary collaborations can lead to very productive results. And that's why I'm really happy to reaching out here is to seeking different collaboration opportunities. Okay. After that, I would conclude my presentation and open for questions. Thank you very much for joining me today.